Okay, so this is the outline of my talk, and the middle I said least squares, and the final part would be about parameter-dependent eigenvalue problems. So this is something recently I'm trying to do, and in particular you will see some application to virtual finite element. I'm not virtual element. I'm not working on virtual element, but for some reasons I attended a seminar, and it gave me the idea of doing this part of the talk, but I will show you later what it's that about. So introduction. So I did something about Maxwell, so just to start from the application, but then everything will become much more theoretical and abstract. But I mean, this is the main application I had in mind when I started working on eigenvalue problem. Maxwell's eigenvalue problem is very common that you eliminate one of the two unknown, E or H, electric and magnetic field, so that you get the curl-curl problem. So I think this is probably well known in this audience. So this is the problem. So this is the strong form of the curl-curl eigenvalue problem. So you're looking for a frequency lambda and an eigenfunction u such that curl of mu inverse curl u is equal to lambda epsilon u in omega with a divergence-free constraint in omega and a boundary condition of the tangential component on the domain. Okay? This is very well known, and in the language of differential forms, you need discrete one form in order to approximate this problem. I mean, just to have some connection with the workshop we had last week. But let's see, I mean, for this representation, I take magnetic permittivity equal to 1. Doug said last week that he doesn't remember which one is which, but I don't know either, but I take them 1, so I don't have any problem about that. And so the standard variational formulation of this problem is this one here. So you consider the space H0 curl, so you mean vector fields in L2 with curl in L2 and boundary condition that makes sense in the distributional sense. So the tangential component is 0 of the boundary. You multiply by test function B, integrate by parts, and you get curl U, curl V equal lambda UV. Okay? And then the divergence-free constraint can be imposed in the weak form by saying that U is orthogonal to gradients. And I also take trivial topology here for simplicity. So what is commonly used for the approximation? This is the starting point of my research on this field, I would say 15 years ago, maybe a little bit more, maybe almost 20 years ago. And was that if you just forget about the divergence-free constraint, which is usually difficult to impose numerically, this problem is equivalent to the original one. The only difference is that you have an infinite dimensional kernel corresponding to the space of gradients. Okay, so just adding gradients thanks to the Helmholtz decomposition if you drop the divergence-free constraint from your equation. So then people said, well, just forget about the constraint, solve the curl-curl operator, and then look at the frequencies that are different from 0. And this at the continuous level is exactly the same as what you do if you consider the divergence-free constraint. Okay? So let's see what happens if you do that numerically. So we start with a very easy example in 2D, a square, so that we know the exact solution. The exact solution corresponds to the Neumann eigen solution of the Laplace problem. So this is m squared plus n squared with m and n positive. Then the eigenfunction are just the curl of the eigenfunction of the Laplacian. So this is very well known. And of course, you have to take care of the infinite dimensional kernel. So we know that there will be a lot of zeros, and you want to forget about them and consider the others. So this is what happens if you consider standard P1. On a general mesh, you take pieces linears, and this is what you get. It's really impossible to use this method, right? Because you have a lot of eigenvalues. These are should be the correct one, the level of the correct one. And if you zoom, for instance, I think this is a zoom of this one here, I think. You get that at the level 1, you have 2 frequencies. At level 2, you have 1. At level 4, you have 4. You have 2. But you have many others, spurious modes, that don't have anything to do with the correct solution. And this is related to, this is what engineers were saying, to a bad approximation of the 0 frequency. This is what people told us. And if you look at the eigenfunction, indeed, you find that there is something good or something bad. So these are the 2 good corresponding to 1. Well, it's just a mixture of the eigenspace. Right? One should be vertical, the other should be horizontal, but there are a combination of the 2. Then the previous one is bad, the one after is bad, and this corresponds to these 4 values here, the 2 with the marker, and the one before, and the one after. So if you look at the eigenfunction, you recognize the correct one. But, well, this is not a good method that you need to look for all the eigenfunctions to understand which one is the correct one. Okay? Then there is some special mesh. This is what is called Powell-Sabin mesh, and this has been observed by Wong and Sanders in 1989. And if you compute the same problem on this mesh, you get some zeros, exactly zero, depends on the level of refinement of your mesh, and then you get some positive eigenvalues, which are good approximation of the correct ones, with a good also order of convergence, second order of convergence. Okay? And this was an observation by Wong and Sanders, and they claimed, well, since this mesh supports some C1, P2 finite elements, then the gradient of C1, P2 are continuous P1, so you have the zeros that correspond exactly to approximation of the gradients, and for that reason, you have good approximation of the correct eigenvalues. This was the statement in this paper here. Okay? This was not a proof, of course, it was just an intuition. And last time, I think I presented these slides, I think it was in Paris in January, when Doug invited me there, and they said, I would be happy if someone can have proven me that this is good. Okay, it's not surprising that this is related to the commuting diagram or to the Durham complex. These are the main references in this field, but of course, I mean, the FIG coming from this seminal paper by Doug is in this picture. In 2D, this is the Durham complex, so you have a subspace of H1, you take the gradient, you go in H curl, you take the curl, you go in H div. At discrete level, you have nodal finite elements, these are the elements we're interested in. Then you take the gradient, you go into in H curl, you take the curl, you go in H div. These are complex in the sense that the composition of two of these operators is zero. They are exact in the sense that this V splits exactly in two parts, the one that comes from the left and the one that goes to the right. Then you have this projection from the continuous to the discrete level, and all these diagram commute. Okay? So this is some magic that is embedded in all mixed finite elements, in particular in the finite element exterior calculus. Okay? This picture has to tell you that in this recent paper by Johnny Guzman, Lischke, and Michael Neelan, Johnny was here last week, they proved that on this mesh, the Powell-Sabin, then you have exact sequence, and you can construct locally some interpolation that satisfies that diagram. And when I attended their talk, it was a few weeks ago in Krakow that Michael actually was giving this talk, they were aiming at Stokes, because construction did these special elements for Stokes, so giving the possibility of having exact divergence-free elements for Stokes. This is good, of course, everybody knows that people would like to have divergence-free point-wise elements for Stokes. And, well, this observation makes it possible to relate everything with also Maxwell and give a justification of the fact that on this mesh, you have a good approximation of the eigenvalues. Okay? We are still finishing everything, but I think everything should work. And this is another example of application of the same result. This is another Powell-Sabin mesh, but starting from a non-structured mesh. So what is a Powell-Sabin mesh? So you have just triangulation of your domain. Then you put one vertex inside each element. Take the barycenter if your original mesh is smooth enough, is regular enough. And then you connect all these additional vertices in such a way that you get straight lines going from one element to the next one. Okay? And you get another final mesh. This is an example. If you compute this, you get very nice results. I computed also on the L-shaped domain, you get nice results, and you get a very good convergence with a number of zeros, and everything works beautifully. Okay? Okay, so the question is, were Sanders and Wong right, stating that if you have a mesh that supports gradients, then you get good convergence of eigenvalues? Well, let's see another compatible mesh. This sometimes is named Powell mesh. All these meshes come usually in contour plotting, because you want something smooth, you want some C1 approximation or something like that. So this is a crisscross mesh. If you look at the results, this is what you get. And I was young actually when I was computing these numbers, and I got this. So I got a lot of zeros, which is correct because you have gradients, so you have zeros. Then you have 1, 1, 2, 4, 4, 5, 5. Then you have 6. Well, 6 would mean that square root of 3 is integer, right? But it's not, because you have m squared plus n squared. And then everyone was telling me, check your code for bugs. Are you sure that the boundary conditions are imposed correctly? And I double-checked everything, and it was tough, actually, but this is what I had. I mean, I had a spurious mode here converging to 6, and I had 2 spurious modes converging to 15, then I had also other spurious modes converging at higher frequencies. And if you look at the eigenfunction again, so you see the correct one, this is the 6, the one that converges to 6, and then the next one, which is good. So this is, you can recognize something related to a checkerboard structure, something oscillating with the frequency of the mesh. And this was not a bug in the code. Actually, then we proved that you must have something wrong with this approximation. And in order to understand what's going on, now I have some nice computation that I show you that I think shed really some light on this example, and also give you, I hope, some idea, if you've never worked on eigenvalues, what is the difference between eigenvalue approximation and standard source problem approximation. So this is what the crisscross element is related to a mesh of squares. So just squares divided in 4 by the diagonal. So let's look now at an element on squares, which are easier to deal with because they are tensor structure or something like that. So just Q1, so bilinear finite elements. If you don't do anything particular, you get something bad, like with the P1 on non-structured mesh. So nothing that can use for the approximation. But if you project the curl onto pieces constant, okay, so the curl of Q1 is not constant because you have something non-linear, it's bilinear. But you can project onto constant, you get something reduced here. Then Riccardo Duran, I forgot to mention that this is a joint work with Riccardo Duran and Studi. Riccardo Duran was able to prove this exact formula for the eigenvalues computed with this scheme. And came to us telling us, well, I proved that the eigenvalues converge. Okay. I was young, I had to code everything, I tried to code, because this formula, I mean, if you compute the limit when h goes to 0, you get exactly m squared plus n squared. It's a very easy exercise. Yeah. So I computed everything, and I might have probably done, again, something wrong with the boundary conditions, because I got the spurious eigenvalues also in this case here. I got this 18, that is not actually a spurious eigenvalue, but it's a spurious multiplicity, because 18 is supposed to be simple, and I got 2 of them. And then we had the formula. We had the proof this time that everything was converging. Well, but sometimes proof seem to be correct, even if they're not. So if instead of taking the limit when h goes to 0, you link h with m and n, so you're not aiming at the pointwise convergence when you fix m and n, but some sort of uniform convergence for all the spectrum, you get that the limit is exactly 18. And this is a picture to show what happens. So the eigenvalues should be on a parabola, right? M squared plus n squared. This is what you get out of the formula from Duran, which is approximating a parabola in some sense, but up to here, not for the tail of your situation. This is the diagonal of this picture, just a section. And so this is what happens, right? So this is the section on the diagonal. The red are the correct one, and the black one are the one they're approximating. So if you fix one value here, and you let h go to 0, you converge pointwise to the correct one. But if you look at the entire spectrum, you have this tail here, and this last dot here converges to 18. So now when you compute your spectrum, you don't see this picture. You just get the numbers that you get from the code, and you sort from the smallest to the highest. And this one is not here, it's there, it's between the others, and you get this 18 that is spurious. So this is the difference between pointwise and uniform convergence, right? And this is actually the difference between source problem and eigenvalue problem. When you solve for an eigenvalue problem, you fix f, and then you find u, and you want your discrete u to converge to the continuous one. This is sort of pointwise convergence. When you solve for eigenvalues, you have to approximate the entire spectrum at the same time, even if you are interested in a small portion of it, and you need some sort of uniform convergence. Otherwise, you may have a situation like this, when something that is outside the windows you're interested in comes in, because you don't have uniform convergence. And indeed, I mean, the crisscross mesh that I showed before is good for the source problem. You can prove in subcondition everything you need for the source problem, but we can prove, and this is also a theoretical proof, that you don't have the uniform convergence, in the sense that you cannot have good convergence for the eigenvalues. And in the case of symmetric compact eigenvalue problems, uniform convergence is sufficient and necessary for the convergence. So what is sufficient is very well known by results by Cato, spectrum perturbation, and so on. The necessity is something that we proved in our paper. Is not so difficult to do. You just expand your solution in terms of the eigenfunction as a Fourier series, and then you show that if you don't have uniform convergence, you can have a spurious approximation.
And yeah, this picture is for that bilinears with the pH.
With a projection.
And now if you put a stable element like a Nedelec element, what would this animation look like?
That you have something that goes up here. It doesn't bend
It
down.
always goes up.
Yes.
You can prove that a stable method can't swing that back down like this.
I can prove that if you fix capital N eigenvalues for h small enough, the first capital N discrete ones are good approximation of those ones, and you don't have anything bad in between. Okay, let's try now. Now we learned that we need some uniform convergence, that the polytopes convergence is not enough. So let's see what I tried to do with the Florian Bertrand from Berlin about eigenvalues for least squares formulation. She works on least squares. She said, why don't we try to do something together? What are you expert on? Eigenvalues. Okay, I'm expert on least squares. Let's try to put them together and see what can we combine. And well, when we try to look at the literature, I remember this paper by Bramber, Kolev, and Pasiak. I remember them talking about least squares for Maxwell. They had a paper for the source problem, also a paper for the eigenvalue problem, but this is the only paper that you can find about eigenvalue approximation. And there is also in Bramble-Osborne, there is a remark about least squares for eigenvalues in an abstract setting, but this a different formulation is not the common formulation for least squares. It's a second order minimization. Usually you use a system of first order equation for least squares. So there is really very little. So even for Laplace, there is nothing. And well, of course, the genuine least square approach would lead to a minimization of something like this. And this is, of course, involves some nonlinearity, but because the eigenvalue problem is nonlinear, so you have a multiplication of lambda and u here. So we are not doing that. But what it started doing is just to try to see how the eigenvalues of the least square operator behave. So you consider the source approximation, the approximation by least squares of the source problem. This gives you a discrete operator, and then you want to see whether the discrete spectrum converges to the continuous one or not. And what is that important for? Of course, this is not important for computing eigenvalues. No one would use this scheme for computing eigenvalues, but gives you some indication of the underlying operator. In particular, is related to L2 estimate for least squares that are not so obvious in general. And it's also interesting for the discussion about the evolution problem. If you want to solve, say, Darcy evolution flows with least squares, or parabolic problems with the squares, if you have a good information about the spectrum of your operator, this gives you also information about the convergence of your evolution problem. Okay, so we consider standard Dirichlet problem, and what do people do in the frameworks of least squares? I think that the most popular least square formulation for Laplace is to reduce to a first order system by minimizing this functional where you impose basically that tau is the gradient of v, and the divergence of tau is minus f. If you put them together, you get that the Laplace of v is equal to minus f. Okay? So this is the usual formulation for least squares. You minimize this. And now you recognize that I'm not working on least squares usually, but I'm working on mixed element because I write the variational formulation for least square the way I like it. Usually people for least squares put them together, the terms that should go together. Sigma minus grad u and all these things, but I write it explicitly like in mixed schemes because it looks more familiar to me. So this is the formulation. So in the first equation you have a term with sigma tau div sigma div tau minus grad u tau, and the right hand side is minus f div tau. And then the second equation is sigma grad v grad u grad v. Okay? This is the discretization. So this is what people did. And you have a very nice theory about that. You can prove that this formulation provides a cursive and continuous bilinear form. In particular, this tells you that you may have by Seas lemma, there is nothing particular, just standard Seas lemma. You get quasi-optimal error estimate like this. So sigma minus sigma h in h div plus u minus u h in h1 is bounded by the best approximation in those spaces of sigma minus tau h and u minus vh. So this is the theory for the source problem. How can you do eigenvalue problem with this? Well, usually if you have f on the right hand side, you substitute f with lambda u, this is what we did. So instead of f, here put lambda u and try to see what this problem looks like. And in matrix form, or operator form at the continuous level, if you want, this is the structure. You have a part A that comes from this part here, the problem. Then you have a matrix B that is minus sigma grad B, and this is the transpose of B, grad U tau. Then we have C that corresponds to grad U grad V. Okay, so this is the structure of the matrix. On the right hand side, this is the bad part for eigenvalues, it's not so conventional. You have a part which is outside the diagonal, is matrix D, that is minus U div tau. Okay. And clearly, thanks to the boundary condition, this matrix D is nothing but minus B transpose. Okay. So you can just substitute this. Okay. And so this is the formulation. And usually, when you have matrices like this, you like to look at the Schur complement. So you solve the first equation by the second equation by y for y, and then you substitute in the first one, and you get this formulation here. So at least we are on the safe side. So the formulation is symmetric, because looking at the original formulation, you might think that we are trying to solve to approximate the eigenvalues of the Laplacian with a non-symmetric formulation. It is not nice, of course. But if you look at the Schur complement, this is nice and symmetric. And if you want to characterize the eigenvalues of this formulation, it's not so difficult to see that they split in three families. Two of them are easy to see. The third one is a little bit subtle, but it is there. So the first family is the, let's start from the end. You have lambda equal to plus infinity for all eigenvectors that correspond to sigma h, because there is no sigma h here involved here. In this matrix, you have 0 and 0. So all y's, all x's, sorry, in this formulation here, they don't provide any u with any eigenfunction. And in particular, since you have 0 here on the right-hand side, by convention, usually you say that the eigenvalue corresponding to them is infinity, because they're divided by 0. Then you have lambda positive, corresponding to the, well, should be the rank of B, not the dimension of the rank of B. It's the dimension of the range of B, or the rank of B, I'm sorry. So it's the rank of B here. And so if B is full rank, by this formulation here, you see that you have something positive definite on the right-hand side here, and this first family corresponds exactly to the eigenvalues of this formulation here, which are positive. And then you may have also some more infinite corresponding to the kernel of B transpose. Because if B transpose has a kernel, then you have some 0 here also on the right-hand side, and you get some infinity. So basically you have three families. So talking in the framework of mixed finite elements, if you have an in-sub condition, so the B is full rank, second family is not there. So you have only two families. One is the good one, the one you're interested in, and then you have the plus infinity corresponding to the variable that doesn't contribute to the eigenfunction. Okay? Then there is also another formulation that you might think of considering, and actually it's been considered in the literature. And since I'm talking about examples and counterexamples, this will be a good counterexample. People also enhance the formulation by adding a penalization of the curl of tau. So since curl is a gradient, since tau is a gradient, its curl is 0. So you can try to add to your functional the curl of tau, you minimize it, so you're enforcing even stronger the effect that tau is a gradient. Now the correct choice of the space is that tau is in H div intersection H curl, and u is again in H1 0. And this is the variational formulation that you get from there. And you have exactly the same characterization of the eigenvalues as in the previous case, with now a different definition of capital A that involves also curl sigma curl tau. So you have sigma tau plus div sigma div tau plus curl sigma curl tau. This is the second formulation. Then you have a third formulation for the squares. So just trying to see all the possibilities. There are also many others, but for brevity, I'm not mentioning all of them. There is the LL star formulation, which is very popular also, which is some sort of an improved formulation with respect to the previous one. The previous one doesn't make sense if f is not smooth enough. You need some smoothness for the f in order to give sense to that definition. The LL star allows also for f in h minus 1. Because here you may consider the duality with H1. The previous one doesn't make sense if f is not in L2. And here you have a more conventional situation where f could also be in h minus 1. So this is the formulation. I'll make the story very short. You introduce L and L star means the L and the adjoint of L, where L is the operator associated with the previous formulation. So you compute the operator of the first order formulation, it's adjoint, you combine them together, and you get something like this.
What's the difference between this one and the first one? Yeah.
This.
No, the one I'm just looking at.
So you have, I call P and Q the variable, and not U and V, because you're not solving exactly manual Laplace U equal F, but you're solving minus Laplace P equal U plus F. This is what you get. I mean, this is in this paper they introduced this formulation, which makes sense, and this is the relation with respect to the previous one. So if you want to solve minus Laplace U equal to F, we are looking for P and P instead of sigma and U, and the two variables that we get out of this formulation satisfy this problem. So the divergence of chi is equal to minus U. Chi is a gradient of P minus U, and P solves minus Laplace P equal to U plus F, where U is the solution of the problem you're interested in. So this is what you find in this paper about this formulation.
Did the previous formulation have F on the first line?
Yes, exactly.
It was tested against a div of
Here, yes, exactly.
instead of against V.
So that's the reason why F could not be less regular than L2, because it's tested against something which is in L2. But here you have F tested against something in H1, so it can be taken in H minus 1. And this is the way to go back to the original formulation from the solution to this problem here. And we played the same game, so we substituted F with mu P now. We call it mu because it will not be the same lambda because the formulation is not exactly the same. And the matrix form now is much better to see because it's symmetric from the very beginning. You also have a short complement that you can compute. It's nice. And here. And here you only have two families of eigenvalues. You don't have the problem of the rank of B. You have the infinity corresponding to the dimension of sigma h again, because here that you have nothing on the first variable. And then you have some mu, which is positive, that corresponds to the dimension of UH. Nice. And then you have to go back to the original eigenvalue problems by using the equivalence that I showed before. And just easy computation shows you that when you compute mu, then lambda can be recovered by this formula. And that if you want to solve for u now, you get that the divergence of chi and the gradient of u are equal to grad p minus chi. Okay? So sorry, u is the divergence of chi, and grad u is given by grad p minus chi. Okay, so this is let's see now the convergence, and I will show you one example and one counterexample in this case. So this is the positive example. So let's start from the first order system. The other one is easier, even easier, but this is the first order system. So as usual, when you want to prove convergence, you need to do two things. First, to show the convergence, which is the uniform convergence of the operator, as I said before. And then you have to estimate the rate of convergence. And part two is easy, just counts on the a priori estimate. What is difficult is part one. And so we introduce the solution operator. Given f, the solution operator Tf1 is just the solution corresponding to the second component of your source problem, so the u. It's just the solution operator of the Laplacian. Given f, the Tf1f is equal to u. That solves minus Laplace u equal to f. Okay. So this is a compact operator, of course. The reciprocal of the eigenvalues, we can call them lambda. They form an increasing sequence, going to infinity. The corresponding eigenfunction ui. Then we have the same at discrete level. The discrete operator is again compact, of course, because it's finite dimensional. The dimension of the eigenvalue, the number of eigenvalues you are computing is equal to the rank of the matrix B, as I said before. And the corresponding eigenfunction, normalizing L2, I will denote them by UIH. And this is the standard theorem about the uniform convergence, that if you know that the discrete operator converges the continuous one in norm, like that, so you can find some rho h going to 0 such that you have this bound, uniformly in F, then you can prove that given a multiple, possibly multiple eigenvalue lambda I, then you have exactly the same number of discrete eigenvalues for h small enough, and how small means that the number of eigenvalues you want to compute should be at least the number of eigenvalues you're interested in, otherwise the space is too small. Then you have exactly m discrete eigenvalues that converge to lambda I, and moreover the corresponding eigenspace converge in the sense that if you combine together all the eigenfunctions corresponding to the discrete values converge to lambda, then this space converges in the sense of the angle between the subspace of the Hilbert space, the gap, to the continuous eigenspace. Okay? So this is the standard theorem that you find in Babushka-Osborne, in Kato's book. Okay, are the standard energy norm for least squares enough to show this uniform convergence of the operator? Well, unfortunately not. This is a part of the counterexample if you want. So this is the estimate I showed you before. So you know that sigma minus sigma h div plus u minus h1 is bounded by the best approximation in h div cross h1. Okay? And we're interested in this estimate here because this is Tf and this is Thf. So we want some sort of uniform convergence of this part here. When f, when your right hand side, is only in L2. Okay? So this is this is what we want. Okay? So this is u, this is UH. We want a bound of this difference in L2 in terms of something that goes to 0 times the right hand side in L2. But this is well known that there is a lack of compactness in this formulation because we are evaluating the best approximation in H div here, and the divergence of sigma is f. So there is a piece of identity in this operator in some sense. Right? So you have the divergence of sigma is f, and here you are estimating f in L2. So if f is only in L2, here you cannot get any uniform bound of sigma minus tau h if you don't get any extra smoothness from, if you don't assume an extra smoothness from f, it's impossible. Okay? So it's not possible to get a uniform bound for this. So the standard estimate don't imply that you have uniform convergence. Well, but we are good because there is some room for improvement because we don't need an estimate for u minus uh and h1 combined with sigma minus sigma h. We only need an estimate for u minus uh and L2. So let's try to do that by using some sort of duality argument. And I think that the first time I've seen this duality argument is in a paper with Doug and Rick when we were doing approximation of distorted quadrilaterals for vector varied functions. I think we did this duality argument for some reasons, and nobody did that before in the least squares community. But it's nice. And so you just do a duality argument by putting u minus h on the right hand side here in this equation, and you try to solve this problem, which is related to the LL star formulation that I showed before, in some sense. And what is the regularity that you can expect for the solution of this problem? Usually you expect u to be in h1 plus s for s larger than 1/2 if you have a Lipschitz polygon or polyhedra. And this is the a priori estimate for this problem here. So p and chi are respectively in h1 plus s and hs. The divergence of chi in h1 plus s, and we divide this into that. And we have this identification with the original problem. Then you do just the standard duality argument by taking the test functions equal to sigma minus sigma h and u minus uh. So you start from the left with u minus uh in L2 square, which is the term that you want to estimate. You use the error equation by adding now the best approximation tau h and vh in your spaces there. And then you use the bound that you proved before, and you can get this. Okay, so you bound this in terms of the product of these two. Okay, but this is something that you can, it gives you the best approximation, and this is something that you can bound by the a priori estimates. And at the end, this is what you get, that t minus th f is bounded by h to power s norm of f in L2. So you have the uniform convergence provided that you have this approximation property for your spaces. And for this space, this is what you usually have. For standard finite elements, this is what you have. And this is what you have for Rabiatoma-like finite elements. I mean, if you have that your chi is in Hs and the divergence of chi is in Hs, then the infimum of this difference is bounded by power of h to the s. Exactly. Okay? So, and then you get the uniform conversion.
And this is uniform for all the eigenvalues.
Yes, exactly. So you have exactly the uniform conversion that you wanted. Okay? Now the question is whether this applies also to nodal finite elements. To start, instead of using Leviathan, people in the least squares community they use also P1 for the sigma. Unfortunately, this argument doesn't work, and so this estimate doesn't give you any uniform convergence for nodal elements. Okay? And the problem is that you don't have any extra regularity for chi than being in HS. Okay? And also other refined L2 estimates that you can find in this reference don't help to show that you have a uniform convergence for nodal elements. And well, I tried to find a counterexample where you get spurious eigenvalues, but I couldn't so far. But when I presented this in Berlin, and Pavel Bocher was in the audience, he told me that he has experience of bad approximation of evolution problem with nodal elements. So I'm confident that more probably interacting with him, we can find some example that triggers this instability coming from nodal elements. So really, this makes a difference with respect to the source problem. For the source problem, these squares, you can use Leviathan, or you can use P1, and everything is okay. For eigenvalues for the evolution problem, it was already observed for the evolution problem that P1 is not so good. So I'm confident that I can find a counterexample also for this. But so far, I don't have it yet. And rate of convergence is the optimal one. I go fast because I want to go to the last part. And just a quick counterexample about the formulation involving the curl. I anticipated that this could cause some problem. And this was actually already observed by Ragnar in his talk last week, that you have this problem, that the space H1 is a closed subset of HD intersection with H curl. And if you have a formulation that gives you a bounded divergence and a bounded curl, and if you're using polynomial that have to fit in this space, so they must be continuous, they are in H1, so they are bounded in H curl inter H div. This means that they are also bounded in H1 because of this closeness. So this means that you cannot approximate functions that are not in H1. Even if your solution is not non-regular, is in this space but not in this one here, your discrete finite element will converge to something that is there. And actually this is what you find. I mean, these are the computations on the L-shaped domain. These is the first, second, third, and so on eigenvalues in terms of the number of degrees of freedom. And you see that the blue one is the first singular eigenfunction that is not converging. This is not a line. This is bending, and eventually will probably become horizontal because it converges to a wrong solution. Because the solution, sigma in that case, is not in H1, and on the other hand, you are approximating something which is in H1. These are the convergence for the good cases. And let's go quickly to the final part. So I said that this part was motivated by a talk I attended about virtual elements. And this is a joint work with Francesca Gardini and Lucia Gastaldi. Francesca Gardini in particular, which was a student of mine, she was the first one proving that virtual elements are good for eigenvalue approximation. And she was giving that talk actually. So she proved that you have the uniform convergence, and then you have all the standard setting, and you have good convergence of the eigenvalues. But she was showing some picture that didn't look very nice to me, and then we started interacting, and I understood at the end why this is the case. So in general, virtual element involves some stabilization parameter. Okay? So the structure of an eigenvalue problem for virtual elements is like this. So you have a generalized eigenvalue problem where both matrices on the left-hand side and the right-hand side are made of two parts. The one that is called consistency part, and the one that is called stability part. So you have A1 plus some parameter alpha A2, and then you have B1 plus some parameter beta B2 on the right. Basically, A1 and B1 are the terms that you can compute in terms of your boundary terms in the element by using polynomials. And A2 and B2 are the remaining part that takes care of what is inside that you don't know how it is because they're virtual. Okay? And this is the formula. So element-wise, this is what you do. For the grad U, grad V form, you have this part here, which is the consistency part. You consider some projection of UH, and then you add what is left, what is not considered by the projection. And the same for the mass matrix on the right hand side. So you have a UV, which is written in terms of some projection, and then you add some stabilizing term. Okay? And then you have to make sure that your stabilization matrices are between certain constants. So this is the crucial part of all theorems. So if you have that your stabilization matrices are in this range, then you have good convergence and so on and so forth. And this is what was proved for the source problem, and this is what also is proved for the eigenvalue problem. So Gardini proved a nice theorem with Varka, I think it was here, and then there are also these other references about the eigenvalue problem, where she said, well, if the stabilization matrices are like this, then we have optimal approximation of the eigenvalues, we have a uniform convergence, and so on and so forth. Okay, let's see.
Is the value of the constants critical here, or?
This is what I'm trying to explain to you now.
Sorry.
That's why parameter-dependent eigenvalue problems, because you really have parameters on both sides. And here I will focus in particular on the parameter on the right-hand side, not the one on the left. But you can also play the same game with the left-hand side. So let's see some numerical examples. Square, Laplace. These are the first 4 eigenvalues. You see only 3 of them because 2 are superimposed because it's multiple. And I fixed alpha equal to 12, and I let beta vary. Okay? You get very nice numbers. Everything seems to be very nice. Let's go now for a larger value of beta. This is what you get. Well, there is also another eigenvalue which is here, but it's not the 4th one. So the picture here plots the first 4 eigenvalues. Okay? These are the first 4. Of course, you notice that it's not so nice. Let's compute more eigenvalues and see how they look like. So these are now the first 20 eigenvalues computed for different values of beta. Mysterious, you don't know what it is about. And the horizontal lines are the correct one, the ones you want to approximate. Okay? What's going on? So this is some theory, very quickly, very basic theory. Let's consider just a matrix eigenvalue problem like this, with the same structure as the one that we have seen before, and suppose that the matrices are symmetric, positive semi-definite, and you consider also the kernel of the matrices, and you want the A2 and B2 to be positive definite on the kernel of A1 and B1. Exactly what we play with the virtual element, right? So you have a kernel in A1 and B1, and you want to stabilize the kernel by adding something. Okay? And moreover, you suppose that the action of A2 and B2 onto the kernel of the other one is 0. So they split really 2 families of eigenvalues. And what happens if you fix beta and let alpha vary? You have something like this. So these are the eigenvalues of the A1, B1 formulation. And these are the eigenvalues of, the A1B formulation. And these are the eigenvalues of the A2B formulation that vary corresponding to alpha, because there is a linear dependence with respect to alpha. So there are straight lines depending on alpha. So these are the 2 families that you find usually when you penalize something on the left-hand side in your eigenvalue problem. Let's play the other game now. You let B vary and keep alpha fixed. This is what you get. It's the reciprocal. Because now the dependence is an hyperbola. Okay? It's exactly 1 over alpha with the notation of the previous slide. So when beta becomes smaller, you get something that produces a kernel here on the right-hand side that goes to infinity, like an hyperbola like this. And you see that this picture is similar to what I showed you before, right? And you can also consider a more complicated situation. Back to VAM, this is the picture, last picture I showed before on VAM. But let's connect these dots in a different way. The same dots as before, but connected according to the number of the eigenvalue. So now you recognize a part of the picture where I started from, with many more details. And it's clear that we are reproducing the situation that I showed in the theoretical setting with matrices, right? So we have this parameter beta, and when beta goes to 0, you have all these hyperbola that pollute your spectrum.
Why do they all converge to the second eigenvalue, not to the first eigenvalue?
Here?
All the lines end up at, when you go to the right.
Because I only computed 20 of them.
So that light blue line will eventually go down and you'll get...
Exactly. So if you take one more, you will have another one that goes up here and more and more.
No, what I'm
the limit is
the dark blue line is not being approached, it looks like here.
because I only went up to 200, they have to go higher. You go
Okay,
ahead.
so if you take beta very large, you'll conclude that the initial eigenvalue has multiplicity 25.
Exactly, exactly.
And you know what is the parabola?
And
Is the formula for this parabola?
is exactly 1 over beta. It's 1 over beta multiplied by the eigenvalues of one part of your problem. There is a trick here. I mean, the orthogonality that I showed before, I think I have to stop, but the orthogonality that I showed before is at the element level. This pi and identity monopolar pi. When you combine those together on a global mesh, you lose the structure of orthogonalities. But the eigenvalues you're computing remember something about what you did locally. Okay? And what is the behavior when h goes to 0? Because this is what people do in finite elements and also in virtual elements. So this is now fixed alpha and beta varying and different values of h. And you see that if h is not small enough, you get something like this. And if you refine, you have 4 eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. The 4 pictures correspond to the first 4 eigenvalues. And in each picture, you have the 4 levels of refinement that are written here. And clearly, I mean, the fourth one, in order to get a good approximation, so you need h small enough, because if you stick with this h here, you don't get it, right? So you get only in this range when you are on the red mesh, which is 1 over 32, and you get the correct one in this range when you have h equal to 1 over 64. So the parameter beta, which is good for the eigenvalues, depends on the eigenvalue itself. And if you don't know what is the exact solution, I would bet it's very difficult to get the right parameter to figure out which one is the good one. So some conclusion and open questions, but I let you done for now. Thank you.
Okay, thank you. It's good that the speaker has good control on the time.
There is a clock there.
Better than me. Questions? We have time for some questions.
So in the cross case, did you use P1 or P2?
If you raise the degree of approximation, the number of spools reduces and go higher in the spectrum. And we are investigating now this with Johnny and Michael, because we are trying to see whether it is possible to have some connection also with the Scott-Vogelius elements. And it seems like there is some connection, because I tried it before, which is the first degree for which Scott-Vogelius tells you that you have the int sup. And in that case, on the crisscross, I couldn't find any spurious mode. And I couldn't find also on a uniform mesh of right triangles.
Yeah, in that case, P2, P1 is a stable Stokes pair, but P1, P0 is not. So I'm not sure.
It's not, but in this case, it's true that it's not a good element for Stokes. But in this framework, you don't need the int sup for Stokes, but you need an int sup with HDiv norm, not with the H1 norm. And the P1, P0 is good in the HDiv norm, because the part that causes you problem is the one that considers the curve, and not the one with the div. So also the P1, P0, and I think this was proved in the paper by Gunz and Fitz and Gunz.
You had a formulation where people added the curl of tau.
Yes.
So, but then you need spaces of h div intersect h curl.
You use P1.
But then you have an issue, right?
Exactly, this is what.
But I guess there are some paper of Sue Brenner where she uses a non-conforming P1.
For least squares.
I don't know if it's for there, but for some problem where.
Oh, I remember, yes.
You know, you need h div intersect h curl. And
Yes, I remember. Also sort of DG formulation or something
Yeah,
like
so-
that. Yes, I didn't try to. Probably the
Yeah, I
same
think
the
it-
same idea
I
could
think
work.
it worked.
You're right.
We had a question here.
Yes, I have a question because I have in mind an old result by Cato saying that if you have a matrix depending on a holomorphic parameter, which is here beta, then you have a holomorphic dependence of the eigenvalue choice if the matrix is normal, which is the case.
Mm-hmm.
So how do you explain in this respect that you can have this
I think-
concentration on a parabola with a change of multiplicity?
So I'm recorded. I have to be careful what I say. So good that you can read Cato. Because
But the proof is crazy. Huh?
But-
you do not understand the proof, but you can read it. I agree.
But this is related to what is written there. There is a word stochastic eigenvalue problem here. And the analyticity of the eigenvalues depending on parameter or some random variable or something like that is crucial in that case. But for eigenvalues, it is analytic only if you consider all the eigenfunctions and eigenspaces that could cross. I mean, when you change the parameter, you may have a crossing. If you change only one eigenvalue, then you can cross another one, and then you can have a singularity. So suppose you consider the first eigenvalue, and then you have a situation like the first eigenvalue up to a certain value of the parameters like that, and then you cross another one. If you continue following the first one, you go to the other one, and then you have a continuity of the eigenvalue which is not smooth, but the eigenspace is not continuous anymore. But if you want preserved analyticity, you have to combine them together and consider at the same time. So the single eigenvalue is not continuous. It's not smooth. So in that case, you have.
No, but in the normal case, there is a choice of holomorphic. There is an holomorphic choice of eigenvectors. So I do not understand why you can have not a crossing,
Yes.
but really something concentrating to something with multiplicity, as you prove with your parabola.
So I would be happy to talk to you about that because I have discussion with a lot of people about this issue. So we have examples in which we have crossings. And I also discussed with another person, not exactly in the field of approximation of PDEs, telling me that there are proofs that in cases like those, the intersections are very limited or impossible. Mm-hmm. But there are examples in which, well, we have seen also examples of intersection here in the picture that I showed you before. And other people say that you have a situation like those. I mean, when you have they go very close to each other, but they don't cross really, but they separate and go back, right? But maybe we can discuss about that and give me reference and see, because I want to understand what you mean. Because I mean, the examples that we see, we have crossings. Mm-hmm. But then we have to understand what katos mean and what is the holomorphic. Yes.
Quick question, right?
No.
No?
The question is quick, but the answer will be long. Want to talk afterwards? Or? I'm going to try to push you beyond counterexamples and examples to ask for the least squares and for the VEM. What's the moral of this story? What conclusions would you draw using these for eigenvalue computation?
Well, for least squares, as I said before, I mean, it's just a toy problem. I mean, nobody would use eigenvalue, this formulation that I proposed today for computing the eigenvalues of the Laplacian. But this could be useful, as I said before, to analyze the evolution problem, because when you know how is the behavior of the spectrum of your operator, then of course this influences all the propagation of the evolution.
So does this suggest that least squares for evolution problems are going to have difficulties?
If you use P1 for the sigma, yes.
Yeah.
And in general, for eigenvalues, I mean, probably we were also discussing that before. I mean, if you have a result which looks plausible, don't believe it. I mean, before believing that result, be careful that everything is correct, because these situations are really very subtle. So when you have a convergence optimal order towards something, every numerical analyst will think that this is the correct result. Right? But this could not be the case. So,
and the least squared people, they introduced it because they said, oh, these mixed finite elements have supercondition is too complicated. We just want to use P1. But then to make their method work, you have to use the mixed finite elements.
Partly.
That's what you're saying.
Okay. So thank you again for your talk. Thank you everybody for being here. And yeah. Thank you.
And now,